Okay, let's try to calculate the torque in the case where the loop, the orientation of the loop is not in the YZ plane, but it's rotated with respect to the Z. It's rotated about the Z axis a certain angle, so it's no longer in the YZ plane. Will the torque be the same or will it be different? So let's calculate first the force on the top side of the loop. So the force, you get it by IL cross B. L1 is the vector from the beginning of the part of the wire you want to discuss, and the ends on the end part of the wire you want to discuss. So the L1 vector points from here to here for the top side, and you get L1 crossed into B. This needs a bit of imagination how to get the cross products. If you think about it or try to make a model in front of you, XYZ axis model in front of you, and you can see that L1 cross B is downwards. It's pointing down on the minus Z direction. If you want to think about it more carefully, look from above. If you look from above, so in this orientation, the x-axis is down, the y-axis is to the right, and so I'm looking above, from above, looking down in the minus Z direction. The magnetic field is in the J direction. Then you can see the L1 vector is pointing from here to here. This is the top side. Looking from above, I can only see a rod here. I don't see the whole loop because it's in the plane that's perpendicular to the screen. So the current comes out of the page here. It goes like that, and then it goes into the page here. So if you can see then very clearly here that L1 crossed into B is pointing into the page, which is the minus Z direction, which is what we showed before. Okay, what about the force on the bottom side of the loop? Well, the bottom side of the loop, the L vector, you need to get the L vector first. It points from here to here. And then L3 crossed into the magnetic field will give you something in the Z direction. And if you want to imagine that again, go back to this top view. The L3 vector in this case is pointing from there to there on the bottom side of the loop. So you can see clearly from here that L3 crossed into B is in the positive Z direction. So these are what the forces look like on the top and the bottom sides, and they don't contribute to the torque. The total force is acting at the center, and when you get R crossed into F, you get 0. These forces are not trying to rotate the loop. So the forces that we are interested then in is the force on the right side of the loop. And so let's get that first. Well, is the force on the right side different than it was when the loop was not rotated? When the loop was in the YZ plane, is the force going to be the same on this side or is it different? Does the force change when this angle changes? Well, the force doesn't change at all. Why? Because I is the same as it is. It hasn't changed. L4 is the vector from here to here. It's pointing in the Z direction always. No matter how much this loop is oriented, this vector always points in the Z direction, and it has a length A. So it's the same vector always. And the magnetic field is always pointing in the J direction. So the force vector, the force on side number 4 is exactly the same as it was before. And it has a value minus IAB in the I hat direction. So let's look at the torque. If you look at the top view, looking down on the Z axis downwards, the R4 vector is this way, and the F4 vector is in the minus I direction, and the angle between them is this angle theta. And so if you want to get the torque on side number 4, it's R4 crossed into F4. The magnitude of the torque is R4, F4 sine of the angle between them. R4 is this distance, and this distance is just B over 2. And F4 is IAB, the magnitude. You can put those values there. And the only difference between this answer for the magnitude and the answer we got before is this extra term of sine theta. So in the initial case that we had before, the angle was 90 degrees between R and F. So sine 90 was 1, so you just had a 1 here. But now when the loop is rotated, this angle is no longer 90 degrees, and you have a sine theta here, extra term, multiplied. What about the direction? Well, if you get the R4 vector crossed into the F4 vector, it'll give you something pointing in the Z direction. And so you get in the K hat direction. So this is what the torque looks like on side number 4. and there's the R4 vector, there's the F4 vector. The torque points in the k direction, and it has a value of this magnitude. And the only difference, as we said, between this and what was before is this sine theta term. What do you expect the force and torque will be like on the left side? The torque should be the same because the force is trying to do the same thing exactly as the other force was trying to do. And the force will be the same force as it was before when the loop was in the YZ plane. So let's see. Again, the force on side number 2, it's I L2 cross B. I is the same as it was when the loop was rotated. It doesn't change. L2 always points from here to here in the minus z direction, and it has a distance a. So it's exactly the same no matter what the orientation of the loop is. The magnetic field also is pointing in the j direction. So the force is the same exactly as it was when the loop was not rotated. So the force is IAB. But for the torque, if you look at the top view, when you get the R2 vector and then the F2 vector, let's get the magnitude of the torque. So it's R2 F2 sine theta. The theta is the angle between R2 and F2. Now the value of R2, this distance, is B over 2. The force is IAB. So substitute the R2 and F2, and it gives you exactly the same value as we got before without rotation except for the sine theta. What about the direction? Well, if you get R2 crossed into F2, you'll get a vector pointing in the k hat direction. So this is what the summary is then for the torque on side number 2. It's exactly the same as the torque on side number 4, and so when we get the total torque, we'll just add them and we'll get twice the value. The half will go, and so we get I small a small b times the magnetic field times sine theta. A times b is just the area of the loop, and so we get exactly the same result as we got before except for this sine theta extra term multiplied. And as we said before, if you put your thumb in the direction of the torque, then the fingers will tend to rotate in the direction that the object will want to rotate. Exactly the same as we did before.